All right, this lecture is about viscosity. Okay, let's create, let's imagine, if you will, a insane scenario here. Let's say you're in a large city, say Dallas, New York, Los Angeles, and you're driving along the road and you notice something. Well, let's make it even more. Here is your middle lines. Then you have another lane of traffic here. So these are lanes of traffic, so to speak. Go ahead and put a red line down the middle of each one. So you're out on a superhighway. However, at the same time, right over here is a parking lane. So here are people that are parked along the highway. Obviously, their speed is, the velocity is equal to 0. So there's some other traffic going this way, but there's a huge barrier here, concrete, to keep people from ramming into each other. Now, imagine, if you will, the speed limit is, say, I don't know, 100 miles an hour. Or say 120. So here's a car running 120. First thing you got to ask yourself, do you think these people are going 120? So you have a car flying along here, and they're going 120. The chances are no, because they know there's somebody driving in here looking to the right for people that are going to pull out and move into their lane. So the fact of the matter is, there is a probability people come out of the shopping mall, which maybe exists right here. Now, this is something you'd never see, and it's obvious why, but it is something good to talk about because there is something related to viscosity here. So people are walking out of the mall, getting in their car, and the first thing they're going to do is they're going to pull out and get in the traffic here. This person, there's no way they could be going 120, so maybe they're going 20. Maybe these guys are going, maybe these guys are running along at 40. There's another lane that's maybe moving at 60 miles an hour. Another lane that's maybe moving at 80. And maybe this lane of traffic's moving at about 100. Why is it that there's a gradient of speed here? If you plotted this, you'd have like 120 up here, and you'd have, say, 0 right down here. And what you'd have is you'd have approximately a linear gradient, or in the case I've come up with, it would be a linear gradient, in which, if you look at the speed as a function of the lane, you'd see something like this. Now, what is happening, and why isn't that you couldn't go 120? Just because of the nature of this, you're constantly looking this way for people to come into your lane. They are actually exchanging momentum with you by coming out of this lane and coming into your lane. So there's an exchange of momentum. Now, what happens when you are over here in the 120 and want to move down? What happens to you is you're sitting in here and you look in your rear view mirror back here. Well, I have to correct that. No, you don't do that. What you're doing, oh, I raced the car. Here, let me put my car back. Since you're going faster than this guy, okay, these people are looking off in this direction, and if he wants to move into this lane, he has to look back here because there's somebody could outrun him and rear end him. So if he's going to rear end someone, he's going to be looking who he's going to rear end or who's going to rear end him. If he's moving across this lane, he's going to look back to your left. Moving across that lane, he's going to look up here. So the same thing occurs here. He's going to basically look in this direction. He's going faster. He's going to have to slow down. If he moves into this lane, which maybe he does, So he moves into this lane. He's immediately got to drop down to 100 or he's going to rear end this person. Now, if you were ever in this driving scenario, you would probably feel a lot of stress because you're in a lane, and as long as you're moving in that lane, you're okay, but people have to park, people have to move along. So if you want to go fast down the highway, you want to get in this lane here. If you want to park, you need to start shifting over lanes ahead of time and moving into your parking zone. So if you're going to park, you're going to basically come along and slip in here. There's going to be a lot of stress in here. So let's create a term that has something to do with stress. Now, obviously, this is a tau, and that's been used a lot in your past as an indication of stress. Now, let's come up with a different scenario. We'll move it down, but we'll move back up here. The different scenario is we have all of these lanes of traffic in which all the lanes are moving at exactly the same speed. And you know that. This is probably something that's humanly impossible because humans are not exactly predictable. But if this did occur and you were driving along, if you needed to shift across 10, 20 lanes of traffic, all you got to do is you got to look in this direction. You don't need to look back. You don't need to look forward. You just need to look across and say there's an exit right here, and you swing all the way across and take the exit. Now, if you knew around you that this was the case, if you knew this, your stress would be pretty much zero. Now, I'm talking about the stress of the driver right now. So your stress of your driver is pretty low because you know you can shift off and shift lanes. You could be just driving down the road doing this the whole way. And for that matter, if you looked straight to your left and straight to your right, you could start doing that. So I would contend that the stress of the driver is related to the change in the velocity for the lanes. Now, as it turns out, that traffic flow and fluid mechanics have a lot of similarities like this. Now, the only difference between a fluid and traffic is humans are involved here, and they're unpredictable. And over here, it's a very predictable process. So the modeling of fluids is pretty accurate. The modeling of traffic using fluids sometimes is not exactly there. But the philosophy is the same. What you've got is particles, mainly cars, moving around, ramming into each other, exchanging momentum, and they're doing it on different layers. So imagine now that, here, I'll go down in here and erase this. Imagine, if you will, a particle. Now, imagine, if you will, these particles in a liquid, for say. So here's a series of particles. Here is a wall. The particles closest to the wall are not going to be moving that far. But imagine that you shove the top layer of the wall at, say, 120 units per second, whatever the units are. Up here it was miles per hour. Down here it could be whatever. So this is a velocity. So a particle is actually moving along, but if you go and look at something called Brownian motion, you'll see something like this. Now, if you go to the Wikipedia site and you drag it over, we'll drag it over for a moment and take a look at it. What you see is a description of Brownian motion, random walk, Brownian motion. But what you see is particles that are just running around bouncing off of each other. Now, you can read the articles, and I would suggest it probably be interesting to do so. There's some very unique videos down here in which you'll see the process. There's several people who've done animations, and the key is if you look at these particular particles, they are moving around. Now, the upper layer here that's attached closely to the top is moving at close to 120 units per second. Now down here, this one's really close to the wall. The wall is fixed, so this is much like the parking lane. And this is a lot like the high-speed lane out here near the top. Now, why is this going? Well, someone could have laid a sheet of plywood on top of water and just drug it along. So all the water at the top is moving at 120 units per second. Now, this particle that's sitting here, you know, you saw the Brownian motion. Now, the Brownian motion is simply describing this. You have a particle. You look at that particle. You look at some delta time later, and there's a distribution around this. There's, say, a 80% chance that it'll be somewhere around here. And then there's maybe, say, a 60% chance that it'll be somewhere around here. But it could go in this direction, that direction. It could go in any particular direction. Now, it just so happens that, say, this particular particle is sitting up here already going 120. So what happens to this distribution is it changes, it shifts. You know, I'm just giving a particular case. It may look something like that. So there's a greater chance, probability that it'll be moving towards the right than the left. And so maybe there's an 80% chance it may look like that. But that may be just like the traffic. There's a good chance that they'll shift lanes. If they're near the top, though, this may be truncated. But there is a probability that this car out here near the edge would eventually end up near the wall. And there's a probability the one near the wall may move through these layers, these higher speed layers, to make its way out to the piece of plywood being dragged along here. In effect, what you've got, if you average this over a period of time, you'll end up with a distribution that looks very much like the traffic flow. Now, as it turns out, we did this stress of the driver related to a distribution. If you say this is y, this could be looked at as the lanes of traffic, and this is the velocity, say. Then the shear stress in the liquid or the gas, or let's just say fluid, is proportional to the what you could call a strain rate. Now, if you start putting different fluids in here, what you find out is there is a proportionality constant. And that's the term that is the viscosity. So a more viscous fluid will create more stress for a given strain rate distribution. But this is the equation that has been determined that works in fluid mechanics. Now, here you've got stress of the driver is also equal to some constant, who knows what that is, times the same thing, say. But the thing is the equations are the same. You think about how stressed you would be if you were driving in a traffic zone like this versus one in which the gradient across the lanes is 0. Even if they were moving 20 miles an hour, you wouldn't feel as much gradient from moving across lanes. You wouldn't feel much stress, from moving across many lanes. So this is a good way of thinking about what happens in a fluid, and where this equation comes from, so to speak. I would encourage you to go read that little bit about Brownian motion. For that matter, viscosity, there's a section of viscosity in Wikipedia that is fairly decent. For our case and purpose, or our purpose here, we can stop here and say this is the term we're going to use. This is what we're going to use throughout fluids. Now we've got to figure out a way of measuring our viscosity of a fluid. How would we do that? Let's start looking at the uses of this equation, and that may give us some guide as to how we would measure viscosity. Let's say someone took a perfectly cylindrical jar. Okay, I'll try to do the best I can here. So from the top view, it looked like this. Well, let me try that again. So from the top view, you saw something like this. From the side view, you saw something that looked like this. Move down. Okay, so those are just reference lines. I'm going to delete them in a minute. So you saw something, came down, and had a pin right here in the center, and then it came across here, and then an outside portion, and what happened is this is an axis in which this thing spun against. So here's the centerpiece spinning around this axis. This one is fixed. So this is fixed, and this one's spinning. So what you decide to do is you decide to fill it with a liquid here. So there's a liquid all throughout here. Now, your goal here in this process is to find what this is. But what you have here, and what you have to be careful of here, is you've got a geometry. Let's say this is R, and we'll call this G, like a gap. Now, if I were to clip this thing and roll it out, what I would actually see, or another way of looking at it is if I just looked at, say, a small portion here, moved over to the side, what I would actually see here is I would see a fixed wall that would be the outside fixed wall. And then I would see the inner cylinder moving along here. Now that might be a little too, but I'll move it out a little bit and just say, looks like this. Now there's a couple of caveats here. First caveat is, my drawing is not to scale. R is considerably larger than the gap. If it is considerably larger, I can do this process. I can lay it out and say, well, what I have is a velocity distribution that's linear, basically straight line. If this gap gets a little too big, I have to go into cylindrical or polar coordinates and work this out. If it's small enough, any polar coordinate dependencies are minimal, if any at all. So that being the case, what I've got is I've got a velocity here, which I don't know what it is right now. Now my equation simply says tau is equal to mu times the derivative of the velocity with respect to the y, lanes of traffic, so to speak. So here's my lanes of traffic, y. There's my velocity. I'm assuming for the moment that it's linear, and as long as this holds true, I'm pretty guaranteed that that's the case. So the question is what is the shear stress? Well, it's nothing more than the force over the area is equal to this times the velocity that is right up here over the gap, because the distance here is the gap. Okay, if you really, there's 2 or 3 ways you want to do it. One is if you want to look at it like this and say it's linear, you could say velocity 1 minus velocity 2 over y1 minus y2. And you can pick the outside as being 1, the outside as being 2, it doesn't matter. So if y1 was 0, then that would tell you that v1 would have to be 0. If y2 is equal to the gap, then v2 has to be equal to the velocity out there. So what you would get is a minus v over a minus g. Now if you were to swap these, you would get plus v over plus g. So you'd get the same answer either way you look at it. Now the question is, what is the force, the total force on this outside unit, and what is the velocity? Well, this is not that hard to figure out. First of all, the velocity is equal to nothing more than omega r. And the torque that's placed on this, because you have to have a torque to get a speed. If you don't put a torque on this axis here, nothing's going to happen. So the torque is equal to, if you just want to do it without make them in vectors, it would be just the force times r, because you know that the point of application here is at the edge, and you know it's 90 degrees from the vector. In other words, this vector is always 90 degrees from the r vector. That being the case, you got a situation where you can put these 2 equations into this equation, and for force you can put torque over r, but that's also over area, is equal to omega. Velocity is nothing more than omega r over the gap. Okay, now the next key that's very, very important here, your first tendency may be to use pi r squared times, say, a length here. If that were your tendency, you would be wrong, because pi r squared, that gives you units of volume. That's not units of area. Turns out what you have is the perimeter. The area is the area of this body here that contacts the fluid. Now, with the exclusion of this area right here. Now, why? Because, again, the gap, the distance from here to here is very small, and this was designed so this was very, very big. So there's very minimal shear stress applied along this surface as compared to along the outside edge. So it's 2 pi times the radius. That is the outside perimeter. So if you start here and you move all the way around this cylinder and you come back, that is the length there. And then you multiply that length times L, and that gives you the area of the object that touches the fluid. Or what they'll usually say is this is sometimes the wetted area, the area that's wet, so to speak. You put that in there and you get a torque, 2 pi RL times R is equal to mu omega R over a gap. Move it down a little bit, and you have to remember the goal here is to find that. So you just want to move this stuff over. Torque times a gap over Now you have to pay close attention. You have 1 r, 2 r's, and 3 r's. But you have a 2 pi r to the third. Now you have an L, and you have an omega. Now, this could be represented in other ways. There are other ways to derive this. That is based upon the fact that they included there's an R inside and there's an R outside. But if you really look at it and you're assuming that this is the case, that R is much, much bigger than the gap, the difference in the calculations is way down in the decimal places. So essentially you get the same answer. So let's look at units first. Torque. Let's go use British gravitational. Foot-pounds. Gap. That's going to be in feet. 2 pi. That's going to be, this is a length and a length squared, so that's going to be feet to the fourth. Now what is this? Radians per second. Now radians don't have any units to them. Radian is just the ratio of a circumference to a radius. So it's a ratio. So if you look at this, I got pounds. These 2 feet knock out 2 here. Feet squared second. Now does that make sense? Let's take a look at the original equation. Tau is equal to mu velocity over gap. And you look back there, this is pounds per foot squared. Usually it's in psi, but it's the same unit. And then this is velocity, feet per second, and then there's your gap, feet. This knocks that out. You move the second over and you get pounds second over foot squared. Pounds second over foot squared. Now I've made a mistake here because this was 1 over, so this second needs to be moved in the top location. So it's a good thing I did this to fix it. So is that the case? And the answer is yes. So now that I've done this, let's do something along this line. Let's copy this equation right here and work it for a particular case. Alright, so we copied it down here, and let's look at a particular case in point. Let's say we applied a torque of, say, 1 foot-pound. And the gap, remember the gap has to be pretty small, so it has to be, say, this many feet. Now relating that to the radius, let's say the radius is 1 foot. The length is equal to 2 foot. And in order, once we torque it with 1 foot-pound, we get a speed of, say, 5 radians per second. So again, we need to identify a couple other things here too. There are 2 types of data here. There's geometry data and there's test data. Here's a typical example of the geometry. R, L, and G are fixed. You go buy this piece of equipment, you have a fixed R, fixed length, and a fixed gap. The only difference is you could fill more water and have a larger L, or a little bit less water or fluid and have a smaller L. But these are geometry based. So you go in and you turn this thing on, and so here you are with this device. You turn it on, you put a torque on it. As a result of putting a torque on it, it spins to a certain speed. So to turn on the test, the torque and the speed are related to each other, and that's as a function after you put the liquid in there and turn it on. That's what you get. So this and this are different based upon the fluid that you put in there and several other things. These are fixed. This is fixed as long as you fill it up the same amount. So you go in and put these numbers in here and you end up with 1 foot-pound, a gap of 0.001 feet, and then divide that by 2 times pi times 1 to the third power, and need to put the units in there as well, 1 foot to the third power for right there, then a length of 2 feet, and then the speed of 5 radians per second. There's one caveat here as well, and that is if say your device doesn't read this out in radians per second, it reads it out in revolutions, say, per minute, then you've got to change that. You could go in and calculate this if you want, but I'm not going to do that. You can do that. I'm going to address this issue right now. Let's say somebody told you it was 180 revolutions per minute. Then what you do is you just say, well, there's 2 pi radians in each revolution, and in every minute there's 60 seconds. So you multiply all this out, and of course your minute cancels this minute, revolution cancels that, and you get radians per second, but you get 180 times 2 pi over 60. So if you have the wrong units on the dial, you can change those out. We'll continue in the second part of this, and we'll do some other problems related to this equation so that you get a good feel for the complete use of it.